I will talk about joint work with Mircea Mustață. Every statement that you see that it's not, doesn't have attributions is joined with him. And this is a survey talk. In fact, it's the first part of a double header. Mircea will talk tomorrow. It's one of the survey talks here, and the general theme. So this pointer is not that great. Anyway, the general theme is that we can use D modules, Hodge theory, all of it under the guise of the theory of mixed Hodge modules in order to address various really basic questions about subvarieties of smooth complex varieties. As you'll see, geometric questions or maybe chromological, numerical, and so on. Basic questions that can be attacked with this technology. Okay, so you'll see in a while what I'm talking about. And more precisely, we have a main tool here, namely the Hodge filtration. In the work that I will explain in this lecture, specifically the Hodge filtration on localizations along function, which we've seen quite a lot already in this conference, but also more generally on what's called local cohomology sheaves. Okay, so let me get started. Here's the setup, the general setup, very basic. We have a closed subscheme of a smooth complex variety, and usually we will assume that this subscheme is reduced. We can just make this assumption uniformly. And we're going to look at what's called the local cohomology sheaves of this subscheme. Okay, and in particular, local cohomology associated to the structure sheaf for this talk, or sometimes to the canonical bundle. This will also come into play later on. Okay, it can be defined in general for any quasi-coherent sheaf. And this, I remind you, it's obtained by looking at the sections or the sheaf of sections that are supported in this subscheme Z, and then passing to higher derived functors, as we always do, right? So to be more precise locally, if you have a ring, it's a ring of functions locally, and you have some ideal, then you start with the elements in the ring that are annihilated by some power of the ideal. That's H0, and then you pass to higher cohomology. So just to be very clear from the very beginning, this is local cohomology and not global local cohomology. Okay, so which would be, the passing to cohomology. Okay, this comes up every once in a while when I give a talk on this. Okay, so let's think of it in a more intuitive way. Alternatively, you can think of it as being the difference between the structure sheaf of X and the total direct image of the structure sheaf of the complement of the subscheme in X. Okay, and more precisely, this is going to come up later. There's a little, dichotomy here. First, you have an exact sequence. So here's the basic map from OX to the push forward of OU. And then H0 and H1 appear as the kernel and co-kernel of that map. And after that, the HQ local cohomology is isomorphic to the Q minus first direct image of OU. Okay, now this is a torsion sheaf. It's supported on Z, but also contains the torsion free sheaf. So this automatically has to be equal to 0. Okay, so in fact, we start with at least H1. Here's the simplest example, namely that of a hypersurface. In this case, we only have one local cohomology sheaf, namely H1. And more precisely, we have a short exact sequence where here, this is the usual J lower star of OU, but because we're extending over a divisor, this is the localization that has appeared already in various talks here, the sheaf of rational functions with poles of arbitrary order along D. Okay, and we know what that is locally, right? If we look at the ring of functions on some open set where D is given by one equation, that this is just a localization at F. This is the ring itself, so local cohomology looks like that. This localization model, very basic module. Let's observe right away that local cohomology in this case has a natural structure of D module. Right? Here you have functions, here you have rational functions with denominator of power of F. So by applying various rules of differentiation, these are both D modules, and so is their co-kernel H1 of D. This is one way to think of a natural D module structure on local cohomology H1. Okay, so localizations we understand pretty well. And now the next claim is that in general, for an arbitrary subscheme, you could kind of deduce the structure from localizations only, but in a rather complicated way. Okay, maybe this is one of the lesser known, at least among algebraic geometers, interpretation of local cohomology. So let's say that locally, the scheme Z is defined by an ideal generated by the functions f1 up to fx. Okay? Then for every index set of any size inside 1 through S, I denote by fj the product of the functions indexed by j. So what happens here is that there is sort of a check type complex. I haven't written the differential, but it's, you would easily imagine what it would be. It's in fact a complex of D modules where the entry CP is the direct sum of all the localizations over all the products of length P. Okay? So every entry in this complex is a direct sum of localizations. And these are maps of D modules. And turns out that local cohomology can be identified with the cohomologies of this complex. Okay, so in some sense, we reduce to the localization case, but in a rather more complicated fashion. Okay, it starts pretty easy. Here, I remind you what I already said about codimension 1. We only have a complex like this, and local cohomology is the co-kernel. And here, if you want, you have two equations, and then the complex looks like this. You've probably seen something like this before, and so on. Okay? All right, so this tells us something very important. Having a complex like this, look, its length is equal to the number of defining equations. So this means that local cohomology will always be 0 beyond the minimal number of defining equations. Okay? So we get some kind of bound for when local cohomology is non-trivial. But in fact, it's quite complicated to know exactly where it starts being 0. This is an important invariant called the local cohomological dimension of Z. Okay, so I define it right away. This is the maximum over Q such that local cohomology is non-trivial. All right? And there's a simplification. I mean, it really can be defined in terms of OX. So let's just take that as the definition. So you'll see, I mean, this will appear quite a lot in the talk. This is rather mysterious, but what's not mysterious is the lower bound. We're inside the closed, in a smooth variety, X, and it turns out that you always have the minimum over the non-trivial, the indices or the exponents for which local cohomology is non-trivial. It's always equal to the codimension, which I'm going to denote by R from now on. So this is, you can use some commutative algebra. There's an alternative interpretation of local cohomology in terms of X that will appear later on in the talk. And using that and some results in commutative algebra, you can always prove this. Okay, so it goes from the codimension to this local cohomological dimension, which we don't understand very well. And the simplest case is to have a local complete intersection. This means that the codimension is equal to the minimal number of defining equations, and therefore there's only one degree in which local cohomology appears, namely the codimension. This is what we saw for hypersurfaces. We had only H1. Okay? But, before you get your hopes up too high that maybe it's a good invariant to detect something like this, I mean, it's very far from being true there. So for instance, and I'll come back to this later on, you can have non-local complete intersections where the same thing happens. I'll address varieties with quotient singularities later on. And so, this is a rather mysterious invariant. So for now, all I wanted to say is that we have local cohomology sheaves, they have D-module structure, and they live in this range that we said. Okay? Next, and the main point for these lectures is that, in fact, local cohomology carries the structure of a mixed Hodge module in each degree. Following the tradition of this conference, I will not say anything about mixed Hodge modules, but except in the way that I will tell you what's important from us from this theory, right? I will basically, point out what are the features that are important for us. Okay, so I will tell you something, but it's not so hard to understand this for hypersurfaces again. Let's start with that. I mean, let me just say it like this. Like, if you're familiar with Hodge modules a little bit, to see that there's such a structure is a very simple thing internally to the theory of mixed Hodge modules. So for instance, in this case of hypersurfaces, the localization along a function is just a push forward of the trivial Hodge module from the complement of the hypersurface. Okay, so it comes endowed with this canonical Hodge filtration that appears in the theory of mixed Hodge modules. And because we have this kind of exact sequence that I told you about, where here you have the trivial Hodge module and here you have this new one, this also puts a mixed Hodge module structure on local cohomology. Okay, I promise that I will tell you a lot of features of this Hodge filtration in a moment. Okay, this is just a general intuitive point. And so we can do the same thing in arbitrary codimension by taking advantage of the complex that I just showed you. We have this check type complex where each entry is a direct sum of localizations. They all have mixed Hodge module structure. The maps turns out to be, I mean, this is a complex of mixed Hodge modules. Each local cohomology inherits a Hodge module structure. And so it comes with a Hodge filtration attached to it, which turns out to live in non-negative degree. Okay? We will also, every once in a while, need to, or actually quite a lot from now on, we'll need to consider what's called the right D-module structure, which simply take as tensoring with the canonical bundle. So most of the time, I'll prefer to look at local cohomology of the canonical line bundle along Z, and also the Hodge filtration, which is also this one tensored by omega of this guy. And in the D-module world, there's a convention that you have to shift this filtration by the dimension, but I will ignore that because it has no relevance for the talk. Okay, so let's just stick to this. Yeah. No, I mean, all of this has to be proved all the time, but it's not. And in fact, you have to take advantage of this quite a lot to prove the results that I'm going to say, that you can make various choices for generators, and those are equivalent. Actually, for many statements that I'm going to make, it depends on that. So I'm kind of sweeping this under the rug. I mean, even in the basic theory of local cohomology. Okay. Yeah. Well, yes, yeah, that's right. There is a functor that you can define kind of analogous to this one. I will not get to that, but yes, more or less it's like the trivial Hodge module for the singular variety Z, more or less, push forward to X. Yeah, so another natural functor in the theory, but again, hard to describe. Yes, absolutely, absolutely. And I'll give you another one, but that's not intrinsic, that depends on resolution of singularity. Okay, so, yep. So this is what I wanted to say, that what I will do is I'll give you a long list of formal properties of the Hodge filtration that we deduce either from mixed Hodge module theory or from birational geometry or a combination of the two. And so, it's kind of a few key features that allow us to use it in practice and hopefully will be useful for more and more things. So let's describe it a little bit or list some properties, and then I'll show you later on a few applications, and Mitch, I will show you more. Okay, so the first question to ask, I guess, is what happens when Z is smooth, right? I mean, this is the simplest case, and we should be able to describe it explicitly, and indeed, this is the case. Right? So there's a much simpler filtration that you can imagine on local cohomology, which is, I'm calling it kind of ad hoc, the order filtration. We know that the elements of local cohomology, the sections of local cohomology are killed by some power of the ideal of the subscheme. So let's just take those that are killed by the k plus first power. Okay? If it were a hypersurface, this would be the well-known pole order filtration. And so this extends that. And for smooth subvarieties, it's not hard to show that the two coincide, right? So the Hodge filtration is just this order filtration. And I'll give you a quick idea, if I can use the clicker correctly, right? So, this smooth subscheme is defined locally by an ideal, which now, it's the right size, but also you can think of the functions as being like algebraic coordinates, x1 up to xr. And so I told you that the relevant module is the co-kernel of a map between localizations. And now you can kind of easily compute this combinatorially because these products are now simple normal crossings divisors. And we understand the Hodge filtration on localizations along a simple normal crossings divisor very well. In fact, I wrote it here. It's just determined by 1 over the function by applying differential operators of the right order. Okay, so then you can do the calculations. It's not so complicated. Okay, so the Hodge filtration is always equal to the order filtration. That's the starting point. Then after this, you kind of immediately sort of run into trouble and have to do more complicated things. And one of the very important features of our talks is that this Hodge filtration admits a birational interpretation. So this is the important point that kind of comes from Hodge theory, but in the end complements Hodge theory. By birational interpretation, I really mean a description in terms of log resolution. And in fact, since this is going to come up all the time, let me fix the notation on the board for log resolutions. Exactly what I wrote there. Okay, so I have a subscheme Z inside X. And so a log resolution will be a proper birational map, F, with Y smooth, such that here, I can consider the preimage of Z with the reduced structure. Okay, so this sits over Z, and the condition for a log resolution is that this is a simple normal crossing divisor. Okay, and let me not write also on this board, but we'll always assume, because this can be done when you perform the resolution process, this could be done by leaving the complement of Z unchanged. So we're going to assume that all the time, that we take such a resolution to be an isomorphism over X minus Z. Okay, so this notation will always appear throughout the talk, so I'll leave it there. Okay, so I remind you at the very beginning I said, let's forget about D modules for a second. Just sheaf theoretically, I said that we could obtain local cohomology by pushing forward the trivial structure on the complement of Z. Okay, so you can also do this in the world of filtered D modules, and imagine that you could go this way, push forward by this open embedding, but U is also present upstairs as the complement of E, so you could also push forward over the simple normal crossing divisor E, and then push forward by this proper birational map to obtain local cohomology. So I wrote some stuff here, which is exactly what I said, but in the world of filtered D modules. So there's a procedure for doing push forward, and I also wrote it only. There's also an analogous thing for T equals 1, but it looks slightly different. So let me stick with this. So we need to compute this in some way. And now I'm going to give you the recipe that computes it by this procedure. There's an explicit representative for this construction that we want to use. So here it is. It looks slightly technical at the beginning, but then I'll give you the first example. Okay, so what happens is this. Stick with the notation over there on the board. On the resolution Y, there is some complex A bullet of basically dx modules, right? So if you forget about differential operators, it looks like the ROM complex with log poles upstairs associated to the simple normal crossing divisor D. And you can tensor with the pullback of differential operators from the base. And there's some differential, which is a combination of de Rham and Koszul differentials. And it has the feature that if you fix some order of differential operators, it increases it by 1 as you apply the differential. And in particular, this complex is filtered by subcomplexes, this time of OI modules, that look like this, right? So again, fk of dx, it is, yeah, okay. Fk of dx is the or differential operators of order at most k on x, right? The standard filtration on dx. And so there are subcomplexes like this that sit inside here, and the fact is that local cohomology, HQ, is the push forward, the corresponding push forward of the total complex. And the filtration on local cohomology, this Hodge filtration, is given by the image of the push forward of this subcomplex inside the total push forward. Right? So there's an inclusion between these complexes, which means there's a map between the direct images, not necessarily injective. So a priori, we have to take the image of this map, and this turns out to be the Hodge filtration. Okay, it's a long story, but this is the outcome of this story. And now comes the absolute crucial point in this picture, which is the Hodge theoretic input. We've done a lot of D-module stuff. There's also Hodge theory that comes into play, and it comes into play in the following form. These maps Phi k are actually injected. Even though they didn't need to be, because of the geometric picture, these are actually injective morphisms. This goes under the name of the strictness of the Hodge filtration on direct images of Hodge modules. This is part of Saito's theory. Okay? And as a phenomenon, since this has come up already, as a phenomenon, it's basically a generalized version of the degeneration at E1 of the Hodge to de Rham spectral sequence. Right? So you heard in Takuro Mochizuki's talk yesterday that the E1 degeneration has come up a lot in birational geometry. It's a very useful tool, and this is going to be another way to exploit this, in various forms. Okay? So if you had a space, let's say a smooth space mapping to a point, and you push forward the trivial variation of Hodge structure, this strictness would be exactly equivalent to the degeneration at E1 of Hodge to de Rham. This is a more general form. Okay, so this is all to say that we actually now know that the Hodge filtration is exactly the direct image of this subcomplex. Okay, it's not just the image, but in fact, it is exactly this guy on the left. So let's do some, examples maybe later, but at least the first instances. Okay, this filtration starts with F0, so what is F0? Okay, maybe, don't look. So let's go back. Okay, so here, k is 0, so there's nothing. Nothing here, nothing here, nothing here. You're only left with this right-hand term where there's also OX or OY here, so you're only left with this guy. So F0 is simply the Q minus first direct image of this line bundle of top forms with simple poles along E. Okay? Okay, so now you see, this is an extremely common type of object in birational geometry. You push forward of some canonical bundle. People look at that all the time. In some instances, it's like a multiplier ideal sheaf, things of this sort, right? And in fact, what I was saying there is that you can simplify the picture a little bit, and maybe it's easier to say it that way. Let me do it here, right? So you have, you have something like this. And maybe you prefer to talk about, maybe understand a little bit better the direct images of the dualizing sheaf of the divisor E. But these guys, when Q is at least 2, they become 0, all of them, because of the what's called the Grauert-Riemann-Schneider theorem. It's a famous vanishing theorem for direct images. And so for birational maps, and so it's the same thing as what I wrote over there. Okay, the direct image of the dualizing sheaf of the divisor. Okay, for k equals 1, it gets a bit more complicated. Now we have something on the right, but we also have another term. So these differential forms, or holomorphic forms with log poles, come into play of order -1. There's a two-term complex. We're still taking the Q minus first direct image of that complex, and it is what it is. You'll see a bit later what it's related to. But things get more and more complicated, right? You go to k equals 2, you're going to have a 3-term complex upstairs. You push that forward. What is clear, I hope, for now, is that these forms with log poles and their direct images come into play crucially. So those are also objects that we like, and at least kind of at an intuitive level for now. If we could show that a lot of these direct images are 0 for one reason or another, we'd be in good shape. The Hodge filtration would be simpler, would be nicer. We could tell a lot of things about it, or in any case, would be more comfortable. Okay, so this is going to come up later on. All right, so this is kind of the log resolution interpretation of the Hodge filtration. We're going to exploit it a lot, but you know, this is just stuff about the Hodge filtration. If I want to use it for something, so I want to measure something. I want to measure singularities or some Hodge theory. How do we measure things using the Hodge filtration? Okay, what's the tool? And it turns out that somehow the most convenient, or one of the most convenient tools to measure singularities is to compare it to other filtrations that are easier to understand, but maybe not so good overall. You already saw that in the smooth case, it was equal to another filtration, the order filtration, which was very easy to understand. So this is what we're going to do. But unfortunately, in general, in higher codimension, we have to look at something slightly more delicate. Okay, so I'm going to call this, again, it's an ad hoc name. I'm going to call it the X filtration. Okay, so let's go through this carefully. So I mentioned earlier, local cohomology has another kind of famous interpretation in terms of X sheaf. It's the direct limit over K of all the XQs of, you know, the structure sheaves of the infinitesimal neighborhood of Z into here omega X, right? That's another way to think about local cohomology. So you have a direct limit. Each one of the entries maps to local cohomology. But unless you're in Q equals the codimension, these maps are not necessarily injective. And here, I'm not going to show you any surprises with anything. They really aren't. And so the X filtration is the image of these X into local cohomology. Okay? Sometimes it's much better understood. So let's go back to the example of hypersurfaces. Okay, so here Q is equal to 1. And, well, forget about this for a second. Just concentrate on the right-hand side. This X filtration, I mean, this ideal sheaf is just a line bundle now. Everything is very easy to compute. And it turns out that EK is basically what's called a pole order filtration. Okay? So it's just forms with poles of order at most k plus 1 along D, basically given by a line bundle. Okay? And Saito has shown, he made this observation that the Hodge filtration is contained at every level inside this pole order filtration. Okay? It's easier to say in terms of localizations, because we don't have to divide by this omega X anymore. The equivalent statement is that the Hodge filtration on the localization along a hypersurface is contained in this line bundle, and therefore it has to be equal to this line bundle times some ideal sheaf, coherent sheaf of ideal, which is what we call Hodge ideals. You know, many of you have heard us talk about Hodge ideals over the last few years. It's a very rich theory. It's basically, you know, the theory and the applications of the Hodge filtration in codimension 1. Okay. So let's see what happens in general. Okay, maybe before that, I should say, inspired by this, what we should aim for is to compare the Hodge filtration with this E filtration, the X filtration. Okay? This is what, I mean, the difference between the two are these Hodge ideals, and they're the ones that encode, you know, can be used nicely and encode exactly what happens with the singularities of D and so on. So we should think of EK as the analog of the pole order filtration and compare the Hodge filtration to EK. When you have a local complete intersection, and for now, most of the results that we know are in that case, it really does turn out that this X filtration is the same as the order filtration that I was telling you about earlier. So it's not really a big deal. It's still basically that. So we're going to compare them. And unfortunately for arbitrary z, this is really quite mysterious. We don't know very much for now, except for this fact. This is general. For any z, it turns out that at the 0th step, the Hodge filtration is contained in this aix-filtration. If you reinterpret it by the birational description that I gave you, it's right here. This is the guy in the Hodge filtration. This is equivalent to the injectivity of a map that can be defined naturally between the direct images of the dualizing sheaf of this exceptional divisor upstairs and these x's on the right-hand side. And these are actually the cohomologies of what's called the dualizing complex of Z. Okay, these are the X sheaves that measure the depth of OZ, and they're the entries in the dualizing complex. So you can imagine that this is a very natural map. It's the map that compares the push forward of the dualizing complex, in fact, sheaf here of E, with the dualizing complex of Z. And that turns out to be injective. So this is kind of the Hodge theoretic input here because of that strictness that I was mentioning earlier. But it's a result that was proved independently before by Kovacs and Schweid and was very useful for them, for instance, to study deformations of Dubois singularities and so on and so forth. It's an extremely useful result in practice. Already appears as the first instance of this comparison. Okay, so, all right, so it's there. But what does it measure? Right? I promise you that we want to measure singularities. And so then what happens if they're equal? Oh, maybe before that, sorry, I forgot about this. So here's an example. This is already very nice, something that they obtained as a consequence. You see, if Z is Cohen-Macaulay, so you impose some kind of condition on the commutative algebra condition on the singularities. I told you that these x's measure depth. And so for Cohen-Macaulay, things are as nice as possible. All of them vanish except when Q is equal to the codimension. So that means that the higher direct images of the dualizing sheaf of E are all 0 except for I equals R minus 1. So compared to this one, it's kind of like a Grauer-Riemann-Schneider type theorem, but for closed Cohen-Macaulay closed subgroups. Okay. Yes, please. If Z is smooth, then that guy, so it's only omega Z there on the right. Yes, absolutely. The E filtration for any LCI is the same as the order filtration. And for smooth things, I showed you that the F filtration is the same as the order filtration. Yeah, so you use the V filtration along hypersurfaces. I mean, no. I mean, for arbitrary singularities, we don't know how to do something like that. Yeah, it was quite specific to the case of. And in fact, in LCI, it can still be done in other ways as well, but not in general. Yeah, unfortunately. About the comparison with the, of course, absolutely. So this is very much, but in the hypersurface case, it kind of, this is a bit of an enhancement of that paper, right? That was looking at the Hodge filtration in the more classical sense and looking at the level of the Hodge filtration, how far you can compare them. So Deline had results about hypersurfaces in projective space, like what, this is actually coming up, not about that paper, but what they actually measure in that paper is coming up a little bit later. But yes, that was also about the comparison between the Hodge filtration and the pole order. Absolutely. Yeah, it's coming up. Absolutely, but you're completely right. It's equivalent to being smooth. Yeah. The map follows, but the vanishing is not clear at all. this injectivity is a very strong condition. There's absolutely no reason for this map to be injected. No, I don't think so. No. At least I don't know how to do it. I mean, it needs some serious input, just like Grauer-Riemann-Schneider. I mean, you could, in fact, do another proof using, compactifying, projectivizing, tensoring with line bundles, using all sorts of vanishing of cohomology. I think that in the end, that's related to their proof. You have to do something. Okay, so let's think about hypersurfaces one more time. It's known that it's a well-known fact by now that if they're equal, or being equal, that was the same as saying that that zeroth Hodge ideal is trivial. It is known that that's a kind of a multiplier ideal that appears in birational geometry. Anyway, to make the long story short, that's equivalent to the pair x comma d being a log canonical pair. This is one of the key notions in birational geometry, the notion of singularities. And if you prefer singularities of the variety that we're studying by itself, it turns out that's also equivalent to the divisor d having what's called Dubois singularities. So I won't get into the definition of this notion. Is a little bit not so easy to define, and I think it will come up in Mitcha's talk. I'm not completely sure, but I believe so. But yeah. Okay, so, just imagine something like this. It's very close to having rational singularities. So I think, like if you have a curve in the plane, maybe smooth means rational singularities, but a node has Dubois singularities, and then beyond that, it's bad. It's not even so. Or like a cone over a conic in the projective plane has rational singularities. A cone over a cubic in the plane has Dubois singularities, but not rational singularities. And then if you go to a cone over something of higher codimension that doesn't even have Dubois singularities. So, there is a nice meaning to these, and they're becoming more and more ubiquitous in birational geometry. But you see, for divisor, it's the same as a very standard notion. Well, almost the same holds in arbitrary codimension. More precisely, this equality still detects the failure of having Dubois singularities, but in the Cohn-Macaulay case and not otherwise. If you're Dubois, then this is always true. But the converse, which is more interesting, is if you have equality of the Hodge filtration with X filtration at level 0, then you're Dubois if Z is Cohn-Macaulay. And we got a nice example from Lin Chuan Ma that this is not true in general. Okay, so it measures something. Okay, I'll come back to this. Let me move on. Okay, if Z is LCI, then things are much nicer. If you're a local complete intersection, you only have HR, and we know how to prove that the Hodge filtration is always contained in the X filtration. So this is great. This is what we're after normally. And I told you, this is also equal to the order filtration, but it's a bit more convenient to think of the X filtration. All right, so now, okay, I want a measure of singularity, so this gives us something. It's basically what Duco was alluding to. So to measure singularities, let's measure how far we can go and have equality between the two. Okay? So this has various names for hypersurfaces. Here we kind of, thought hard what to call it for now because we don't know many things, so we just came up with this name, Singularity Index, for the subscheme Z. Well, this is the maximum over K, such that the Hodge filtration is equal to the X filtration. Okay, so you saw that when you're smooth, this is infinity. Maybe I shouldn't call it the maximum, but anyway, it's infinity. On the other hand, this may not even happen for K equals 0, so you may not be Dubois. And then we just declare that it's equal to -1. Okay, anyway, it's there. So let's try to understand this a little bit as a measure of singularities. But before that, let me tell you one result that we can show is that this, in fact, is bounded. There's kind of a uniform bound, upper bound for the singularity index. Okay, so if you're singular, so, it's not infinity, or, or anyway, if you're singular, then it's bounded. That's what I'm trying to say. P of Z is less than or equal to the dimension of Z minus 1 over 2. Okay, and in fact, there's something a little more subtle. It's actually less than or equal to this codimension of the singular local. Yes, yeah, it's true. Yeah, it's almost clear. Yeah, so, and it's a true fact. Once you fix it at level k, then it's true for all the previous ones. Yeah, so you can reinterpret this as saying that they're all equal up to level. Yeah, it's not so hard to do. Okay. Yeah, and that's a very good point. I mean, you really can't extract information from below. Okay, so you have this inequality. And if you think about it, so now I'm really going to write it down as a measure of singularity. So another property of the Hodge filtration, sorry, I forgot to do them successively here. So it looks kind of bad. Let's try to focus on every line. So when Z is a local complete intersection, from everything I've said, it follows that if Z is smooth is equivalent to the Hodge filtration being equal to the polar order or the X filtration all along. Okay, it uses the theorem that I just mentioned. Also, from the theorem that I said on the previous slide, the singularity index is non-negative if and only if Z has these Dubois singularities. And in fact, and we're kind of excited about this. This is something that we've been interested in recent times. This has a generalization that's really neat. That if the singularity index is at least p, then the scheme has p Dubois singularities. Okay, so this is not a joke. I didn't just put a p there in front of everything. There is a kind of a very separate meaning to each one of these sides. This is expressed in terms of the Dubois complex. It's basically an understanding of the hired filtered pieces of the Dubois complex of the singularity, if you're somewhat familiar with that. And you'll see more about this in Mircea talk. So let's leave this aside. Okay, and a recent result by Chen, Dirks, Mustaza, Olano. These guys are here, and this is a current and future Michigan team. They show that if P of Z is greater than or equal to 1, then Z has rational singularity, which we knew in the case of hypersurfaces, but it's really new for LCI singularities in general, and it's very neat, and I'm really looking forward to seeing the preprint. And all of this is part of a general conjecture where we understand what this singularity index should be in terms of the Bernstein-Sato polynomial. So in the LCI case, there's a Bernstein-Sato polynomial that was studied by Budur, Mustaza, and Saito. And it has, just like in the hypersurface case, it has a distinguished root, -r, the codimension. You throw that away. You look at, the next kind of best root of this polynomial or more prominent root of this polynomial. We usually denote it like this, call it the minimal exponent with, by analogy with the case of hypersurfaces. And the claim is that the singularity index is computed in terms of the integral part of this minimal exponent. Okay, so it's determined by the minimal exponent, but then doesn't quite determine it only up to integral part. So that's the conjecture. This then is known to imply this other stuff. I mean, this line here, maybe this line here. And this is known for hypersurfaces as one of the major things about Hodge ideals and the theory in the case of hypersurfaces. This was done by Saito. So he observed, and again, this is something that I think Mircea will discuss to some extent, a connection with the V-filtration of D mod. Namely, he related Hodge ideals to the V-filtration along that hypersurface, and that enabled him, in particular, to prove this statement for hypersurface. And kind of going backwards, now we use the theory of Hodge ideals because it's more geometric to gain an understanding of the minimal exponent of a hypersurface, an understanding of this root of the Bernstein-Sato polynomial, how it behaves in families with respect to restriction, and so on and so forth. Okay? So I guess kind of this much for now as the Hodge filtration as a measure of singularities. On the integral part. Yes, in fact, we do get information about everything, but that's a whole other story, and I'm not even sure if Mitcha will discuss this. You will? He will. Okay, great. So there's for hypersurfaces, we've also developed a theory of Hodge ideals of Q divisor. Maybe in some nice future, there will be something more refined, even in this case. But there we have a Hodge filtration for Q divisors. It's natural to study Q divisors, especially from birational geometry point of view. And so that allows us to recover binary information, in particular truly the minimal exponent. Yeah, like in some sense in the V filtration, you really hit every index. Yeah, but it's not part of what I'm saying. Yeah, it's coming. It's coming. Yeah, absolutely. I cannot give the talk without the generating level. We're gonna generate here for a while. Okay, so yeah, okay, great. But before that, let's see, what do I want to tell you next? Okay, great. So okay, let's focus on what I say first. Okay, so all of this is local. Everything that I explained to you up to now, it's local, right? In the neighborhood of a point, you can do all these constructions. But you know very well that Hodge theory has important global consequences, right? I mean, if you're in a projective manifold or compact Kähler manifold, you have a lot of global consequences of Hodge theory, and one of the famous ones is vanishing theorems for cohomology groups, right? And so in order to efficiently apply this theory, you need to look at this here as well. Okay, and so a major feature of mixed Hodge modules that, Saito didn't consider it to be very major because it was like a passing remark in his original paper. But, I think a major feature of mixed Hodge modules is that all of them come with a vanishing theorem that generalizes Kodaira vanishing. Okay? It's a complicated statement. Here I stated it only for local cohomology, so in our particular case, and it's still a complicated statement. I'm not sure if what I wrote here makes a lot of sense, but this is the statement. So, before I give you some special examples that make sense, let me just say what this means, right? So, X is a smooth projective variety. You fix an ample line bundle, or a positive line bundle on X. Then what you do is you take your mixed Hodge module, or filter D module, any of them, you pass to the de Rham complex, and then that's filtered by the filtration, and you pass to the associated graded pieces of the de Rham complex. You pass to any associated graded piece. Okay, so now these are complexes in the, or objects in the bounded direct category of coherent sheaves. And then the statement is that when you tensor those with any ample line bundle, you have vanishing higher cohomology or hypercohomology. Okay, so at least in flavor, it sounds like the Kodaira vanishing theorem. And in fact, Kodaira vanishing can be recovered from this. Akizuki-Nakano vanishing can be recovered from this. Nadal vanishing, lots of vanishing, almost any vanishing you want can kind of go back to this sort of vanishing. Okay? But again, it looks like a mess right now. How would you apply this? Or rather, what does it really mean? Well, let's look at the extremal case. I take any of these local cohomology sheaves, but I take this index here so that in the de Rham complex, we're left with only one term at the very end. So now it's vanishing about the sheaf, and it says the following, using our birational interpretation. Okay, so let's not worry how I got to this, but this is F0 in the Hodge filtration, so that's all that matters. It's a vanishing theorem for H0. The higher cohomology of the higher direct images of this canonical bundle with poles along E, or if you want, of this guy, like I said, at least when Q is at least 2, is equal to 0 when you tensor with an ample line bundle. All right, so if you were in the case where it's just a direct image, this would be like the Nadal vanishing theorem for multiplier ideals. For higher direct images, Kolar gave a famous theorem about the generalized Kodaira vanishing, about direct images, and in this form, this is due to Fujino. So this is Fujino's generalization of Kolar's vanishing theorem. So again, it's a kind of a well-known tool in birational geometry. It's the simplest case of vanishing for the local cohomology Hodge modules. Okay? So now I can't help myself. I promised you some geometric applications, and it's time to give one. Now that I stated a vanishing theorem, I want to explain to you how all this machinery that may seem really kind of technical and sophisticated can be used for very basic statements. I picked one that's kind of easy to explain. Okay, so that's going to be an application of this vanishing theorem in the local study in the case of hypersurfaces. Okay, so let's specialize this vanishing theorem further to hypersurfaces. Okay. When we have a hypersurface, I remind you it's a little bit easier to work with the localization along the hypersurface. And I told you that the Hodge filtration is given by this line bundle of forms with poles of order at most k+1 times some ideal sheaf we call Ik, the Hodge ideal. And the vanishing theorem takes this form. You can do some more manipulations, and now it looks kind of nice. With no gurs, no derams, no nothing. Okay? It looks like this, right? So X is projective and D is ample. Under some mild assumption, okay, I'm kind of cheating here because I don't want to state them. You have this vanishing, right? If D is ample, right? Or otherwise you have to tensor with an ample line bundle. Okay? These higher cohomology groups are equal to 0. On some varieties, you don't need any assumptions. So in the one that I'll describe, you don't need any assumptions whatsoever. So you see now it kind of looks like Kodaira vanishing more. Okay? And so in the case of Hodge ideals, because we're working on hypersurfaces, the birational interpretation gives us more information than in general. We're able to do something that I haven't talked about at all in the arbitrary case, namely kind of a simple local thing. You just look at the divisor and look at the multiplicity of a point on that divisor. N is the dimension of the variety. And then I pick two numbers, P and K, whatever they are. So if the multiplicity of the divisor is sufficiently large, then the kth Hodge ideal is non-trivial at that point. And not just non-trivial, in fact, is contained in the pth power of the ideal of that point. Okay, so it also tells you a little bit how deep the Hodge ideal is. So it's just yet another measure of singularities, but at a kind of a very basic level. It somehow detects the multiplicity of a point on the hypersurface. Okay, so I want to combine these two statements to give you a result about theta divisors on principally polarized abelian variety. Something completely independent in, right? So this is what Mircea and I proved a few years ago. It's kind of the general case of a conjecture on theta divisors on principally polarized abelian varieties, which is just about bounding the multiplicities on points of points on theta divisors. Okay? The problem has a history. If I gave a talk on this, of course, I'd go through this history, but it has a very nice history. I'm happy to explain it afterwards to whoever is interested. Now I have to kind of just do it. Okay, so we have a principally polarized abelian variety of dimension G, right? For classical reasons, we call the dimension G in this case. And we assume that this theta divisor has isolated singularity, right? This is the general case among all singular theta divisors. And then the statement is that the multiplicity of every point is at most G+1/2. Okay, G is the dimension of A. All right, so this had been conjectured, and in fact, it's a conjecture in general, and it's also known to be optimal. This bound can be attained, and there's a little extra point here that, in fact, if it's attained, it can only hold at one point, but it can. Hyperelliptic curves or the Plano surface of lines of the cubic threefolds, and so on and so on. Okay? So this is the statement. How do we prove such a statement using the theory that I just described? Very simple idea, right? So we're going to take advantage of the Hodge ideal I1. So of the F1 step in the Hodge filtration on localization or local cohomology, if you want. Okay? So we focus on this guy. In fact, it's known that I0 is trivial, so I won't touch it, right? I mean, that's already a statement. It says that A theta is log canonical. But here we look at I1, and if the theorem weren't true, I gave you some bounds here, general bounds about multiplicities. If you read through what this means, a completely general point, if the theorem weren't true, then the first Hodge ideal would be contained in the square of the ideal of the point on the abelian variety. On the other hand, the vanishing theorem for the Hodge filtration takes this form. No conditions needed on abelian varieties, plus the canonical bundle of an abelian variety is trivial. So the vanishing theorem, or a special case of the vanishing theorem, is this. Okay? So you see, I1 is contained in the square of the ideal at that point. It's also with isolated singularities, so I1 is only co-supported at a bunch of points. So the quotient of these two guys is zero-dimensional. So by default, it has vanishing higher cohomology. So you see, I1 has vanishing higher cohomology. The quotient has vanishing higher cohomology. So from a standard exact sequence, you get that the line bundle 2 theta times the square of the ideal has vanishing higher cohomology. And in fact, because you're on an abelian variety and you can translate things, you have the group structure. With a little extra trick, you can get the same thing for all points on the abelian variety. So now it's a statement that has nothing to do with Hodge ideals, with nothing. It's just a statement about the 2 theta linear system, and in fact, it's a false statement. This can never happen, right? I assume that there's a point of high multiplicity. Well, if you've done your homework and done the exercises in Hartshorne, you know that this is equivalent to the fact that the linear system 2 theta separates tangent vectors at each point. Okay, but that's false, right? I mean, the 2 theta map is very famous. It's the Kummer map of a principally polarized abelian variety, and it's ramified at the 2 torsion points. This is a false statement. Okay, so that's basically, by and large, the way in which the Hodge filtration is used for this geometric statement. Water. I want to go back to, so I leave this, let's say, geometry, and I want to go back to the higher codimension case, and I want to explain something more cohomological in flavor that has to do with the Hodge filtration and local cohomology in general, and that's also something that we're quite excited about in recent times. So, and I also want to make Christian happy. Okay, so we're going to talk a bit about the generation level, and then we'll see an application of that to, again, another very basic problem. It has nothing to do with Hodge filtration. Okay, so first, I stated this as another property. Maybe it's really a result, but in any case, by property, I mean it's something that's important to study, to settle somehow, to understand. So for every filter D module, you can talk about the generation level, right? So if you have a filter D module, by definition, that means, so this is a right D module, the way I wrote it. By definition, it means when you take Fk and you apply Fl differential operators, you're contained in Fk plus L, right? This is always true by the definition of a filter D module. But if you have a good filtration, eventually this becomes an equality, and then you just declare that that's, you know, is generated at level K if this becomes equality for that K and every L. So kind of colloquially, you have Fk, and then you obtain all the higher ones by just applying differential operator. So they're determined by Fk. All right, so this kind of log resolution study, so now this notation here will come into play a lot. This kind of setup allows us to give a criterion for the generation level of the Hodge filtration on local cohomology. Unfortunately, not on all local cohomology, but on the one that's interesting if you want to study the local cohomological dimension. Okay, so let's assume that all local cohomology is 0 beyond a certain level. Then at that level, in that degree, the Hodge filtration is generated at level K if you have a whole bunch of local vanishing statements, higher direct images of various holomorphic forms with log poles coming from the resolution of singularities. Okay, so don't worry too much about the exponents. That's not the message that I want to communicate, is that there's a finite number of such direct images. If you checked their vanishing somehow, you understand the generation level. The only thing to note is that, you know, in passing, is that if you make this number large, if it goes beyond the dimension, then of course there are no higher direct images because you don't have fibers of that dimension. So in particular, this shows that it's always generated at level n minus q. But usually you want to do better than that if you. Okay, so there's some such vanishing statements, and I want to show you, I want to finish with an application, right, to understanding the criterion which describes the local cohomological dimension of a closed subscheme in an arbitrary smooth variety. Okay, so let's go back to that notion that I explained at the very beginning of the talk. Okay, so the local cohomological dimension is the maximum over all degrees for which local cohomology is non-trivial. So basically, this is the invariant that understands how much local cohomology we have. Okay, and so this was studied a lot. I mean, there are a lot of very interesting works studying cohomological dimension and local cohomological dimension. Almost 50 years ago, Hartshorne, August, Peskin, and Spiro studied this very much, and it's been studied ever since, and there are many exciting results that are being proved these days, and mostly by people in commutative algebra. There are lots of nice results that are being proved still about local cohomological dimension. Over the complex numbers, the most complete result is due to August from back then, and he gave a topological characterization of local cohomology. So it's a statement, it describes LCD in terms of the vanishing of a collection of singular cohomology groups, or more generally, algebraic de Rham cohomology groups. Okay, I didn't write it down. I mean, it's not very relevant for our talk, but it's been used a lot. And again, it's a topological statement. Okay, and in fact, Peskin and Spiro gave a complete result in characteristic P. And it looks nicer than the one in characteristic 0. Maybe I'll say it later. What it is. Okay, so this theory of the Hodge filtration that I explained to you allows us to give another criterion, a characterization of local cohomological dimension, this time more algebraic, more holomorphic or coherent sheaf theoretic rather than topological. Okay, so the idea is very, very simple-minded. Okay, you have a filtration. So if you want to prove that a sheaf is 0, well, you might as well prove that the first step in the filtration is 0, and then that this step generates everything else. So the filtration is given on level 0, like as simple-minded as it gets, right? Question is whether it works or not. But of course it works, at least at a theoretical level, because one, I gave you a description of F0 in terms of log resolutions, and two, I just gave you a theorem that described the generation level also in terms of log resolution. So, of course, there is a statement, right? And that's exactly what I'm going to... the pictures are... Okay. So, yeah, no, I saw that people were taking pictures. All right, so... okay, so this is what I was saying, right? I gave you a description of F0. In fact, it's right here. And I gave you also a theorem. I just stated a theorem about the generation level in terms of vanishing. So now we have this alternative kind of characterization in terms of a finite collection of coherent sheaves, right? That you check at the closed points of the subvariety, and it looks like this. Okay, so the local cohomological dimension is less than or equal to some number n minus k, right? So it cannot go beyond n. The maximum possible value is n, the dimension of x. Okay, so it's less than or equal to n minus k if and only if, again, you have some finite collection of vanishing statements, local vanishing statements. Rj plus y f lower star of these forms with log poles is equal to 0 for all j greater than or equal to n minus k and all I greater than or equal to 0. Okay, so let's try to see it in action a little bit, right? How can we check in various cases whether these sheaves are equal to 0? Okay, so let's give examples. Yeah? So I will ignore everything that's clear, right? Beyond Rn, everything is clear. It's 0 by default. We're in dimension n. So if you take this criterion, I mean, you look at, I don't know if it makes sense. I'll just tell you what it is, right? So if you want to check that the local cohomological dimension is less than or equal to n minus 1, okay, so what does this mean, right? It could be at most n. So think about this. You take a point on a smooth variety, that definitely has hn, right? N is the codimension of the point, is a smooth subvariety, so hn can be non-zero at a point. Now we want to understand when it's not maximal, so when LCD is not n, and this is the criterion. You have to check the vanishing of one direct image of a line bundle. And now you do the calculation, like you really look at what maps to points, what doesn't map to points. You do some standard calculations with log resolutions, and it's not too hard to check that this is equivalent to exactly that there are no isolated points. Okay? Well, this is a well-known result. It's done even in more general settings when the ambient space is not smooth, but this is a smooth version of what's called the Hartshorne-Lichtenbaum vanishing theorem. LCD is at most n-1 if and only if Z has no isolated. Okay? So it's a completely geometric, very simple criterion in this case. Okay, so the next step is then to understand when LCD is at most n-2. Okay? The very next step is to see when Hn and Hn-1 are equal to 0. All right, and again, you run that criterion, you throw away all the obvious vanishing, and you're left with 3 vanishing statements that you have to check. So LCD at most n-1 is equivalent to these 3 vanishing statements if you fix a resolution of singularities like that. It turns out that the first is always true for any Z for whatever reason. I mean, it can be proved, but it's not, I cannot place it in any kind of pattern whatsoever. It just happens to be true. And you'll see in a moment that perhaps there shouldn't be a clear pattern. Okay, the second one is exactly what I told you. The second one is already what was checked to have it at most n-1. So it's already there if you don't have isolated points. Okay, so we can also get rid of it. So you're only left with this guy. So basically, LCD is at most n-2 if and only if you have the vanishing of this higher direct image, again, of a line bundle on the resolution. Okay, so what do we do about this? This is a little harder to understand. There's some Hn-2 possibly, or other cohomology groups on the fibers. But we have a trick up our sleeve. Namely, I told you that the 0th step in the Hodge filtration is contained in the X filtration. At level 0, we always have an injection from this direct image that we're interested in into an X sheaf. And these X sheaves, like I said, they measure depth. And this sheaf here is equal to 0 even only if the depth at the points of OZ is at least 2. And therefore, you get another well-known theorem, this time of August, that if the depth of OZ is greater than or equal to 2, in particular if Z is a normal subvariety of X, then the local cohomological dimension is at most n-2. Okay? And so you can try to do more and more of this. For instance, so you can go to the next step, try to see what happens if the depth is at least 3. And there's a very nice result which extends this. It's quite recent and is due to commutative algebraists, due to Varbaro in some special case, but he proposed that this is true, and then it was completed by Dao and Takagi, that if the depth is at least 3, then the local cohomological dimension is at most n-3. And we also checked this with our method, but we only had energy to check it for isolated singularities. And, presumably it can be done, but it requires more work. Okay? But it's true. And so you see there's a clear pattern here, right? If the depth is, at least k, then local cohomological dimension is less than or equal to n-k. We know what we have to prove. Well, this is completely false. Okay? So the pattern stops exactly here. And in these papers, there are counterexamples. I mean, you have examples with depth at least 4, but the LCD is, again, n-3. There are some determinantal ideals that do this job. And then you can do it for, in higher values. I mean, it kind of, this pattern breaks down. And it's very interesting that it doesn't in characteristic P. So the theorem of Peskin-Spiro that I was telling you about says that in characteristic P, the local cohomological dimension is equal to n minus the depth. For some reason, it breaks down in the complex numbers in some sense, makes the picture more interesting here. So that's that. And I kind of want to conclude by saying that nevertheless, this pattern does hold in various instances. And based on the study of the Hodge filtration, you can sometimes get, for certain types of singularities, that the depth is equal to, the LCD is equal to n minus the depth. So, but you have to include some extra information. So sometimes combinatorial, sometimes some knowledge of the Dubois complex that will appear in Mircea's talk tomorrow, and so on. But you have, here are some examples. For instance, if Z is given by a monomial ideal, this procedure with the Hodge filtration shows you. So anyway, I guess what I'm saying is that you want this is the ideal result, okay? And of course, n minus the depth is the same as the projective dimension by Auslander Buchbaum. This is known. We found the paper of Dubesnik. I don't know if anyone knows if it was done even before. Is it, do you know, is he the first? Yeah, right, yeah. So this is well known. But here's a new result. The ideal statement works for varieties with quotient singularities. So this uses this criterion that I explained to you, this kind of vanishing criterion, but interpreted in terms of the Dubois complex, and then people understand very well the Dubois complex of varieties with quotient singularities. So it happens that, again, you have a formula on the nose for the local cohomological dimension. It's the dimension minus the depth. These varieties with quotient singularities are always Cohen-Macaulay, so all of this is equal to the codimension of Z. This is what I told you at the very beginning, that you have a situation where, again, you only have HR, just like for local complete intersection subschemes, but in fact, many varieties with quotient singularities are not even Gorenstein. So they're not local complete intersection. And so, hopefully people will discover many more uses of this criterion. And so I'll pass the baton to Mircea and let him tell you more about everything tomorrow. Okay, I'll stop here.
Okay, so thanks a lot for this very interesting talk. Are there questions?
In the case of LCD equal to n minus 2 or less, can you recover the full Hunecke-Lobeznik thing?
Yeah, that's an excellent question. So, no. And this is very interesting. So I kind of avoided this, but now that you're asking, let me say it. So we have an alternative criterion, right? Our criterion is LCD is n minus, or less than or equal to n minus 2, if and only if Rn minus 2 from a resolution is equal to 0. August, with his topological interpretation, obtains a different criterion which says that basically the punctured formal LCD is less than or equal to n minus 2 if and only if the punctured formal spectrum at that point is connected. And that's equivalent to the vanishing of one algebraic de Rham or local algebraic de Rham cohomology group. So we don't know yet how to prove that these two statements are equivalent. We know how to prove one implication, but I forgot which one. Do you remember? I don't know. Our criterion implies his, or his criterion implies ours. You can extend this question. This is a special case of the question is why are our criterion and August's criterion equivalent? Right? So it's a triangle and we know two sides and we'd like to know why the third side is also true. And we don't know yet, and this, I think it's a beautiful research problem. On one hand, you have topological information, algebraic de Rham cohomology. On the other hand, you have holomorphic information in terms of some local cohomology groups of Dubois complexes. So it's kind of like in Hodge theory, right? On one hand, you have the topological spaces, and they have a decomposition as holomorphic spaces. This is a kind of a more sophisticated Hodge theory, and it refers to local cohomology. And we don't know yet why it's true. It's kind of like if you had a degeneration of some spectral sequences, it would hold, but we don't know that that's true. It's probably false. Anyway, the long story short, it's a very interesting problem to understand the difference between the two. I think it's a great thing to discover. And, it will happen.
Are there more questions?
Do you have any conjecture on the generating level as with the Singularity Index in terms of the minimal exponent or related?
Yeah, I guess so. I just don't know how to. I can't write it down by heart.
Put it up.
But surely there must be, right? So, so I guess what you're asking is that, yeah. So this refers to the following. I believe you're referring to the following statement. If you have a hypersurface,
like in the case of Hodge ideal,
in the case of
the Hodge filtration for hypersurfaces.
Exactly, yeah. So if you have a hypersurface, there's a theorem that Mircea and I proved that was proved first by Saito for quasi-homogeneous singularities. We managed to prove it in general, and it said something like the generation level of f on the localization along this hypersurface is equal to, do you think I can remember now? I have no idea. It's like n maybe something like this, n minus 1 there's a chance that it's like this. Yeah? So, okay, so this is yet another way, right? I mean, you see, like, I didn't bring this up at all, but it's another nice appearance of this. Okay, sorry, it's not the generation level. It's, of course, it's generated at this level, right? Lower, like this. Yeah, and it's actually equal for quasi-homogeneous singularity. So in fact, it's optimal. So yes, so this minimal exponent, aka singularity index, kind of, in the case of hypersurfaces, is very much related to the generation level as well. And I suppose why not? I mean, for local complete intersections, there should be some kind of similar behavior, but we know so little right now. I mean, surely that used this whole. The proof of this used the full power of the connection with the V filtration. And this is in progress now to really understand how this Hodge filtration interacts with the V filtration. Is not fully established, if I understand correctly, at the moment. When that is, presumably there will be some statement of this sort. I don't want to venture to say exactly what the formula is. Yeah, for sure. Yeah, that's a good point. Yeah,
Any more questions?
In the paper by Dimka, he also makes some conjectures or pose some questions about this generation level thing.
The paper by Dimka and Delin?
Well, there were some papers before, and my question is whether your conjectures are superseding these. Well, they were quite specific, but I cannot remember.
They must be superseding that. Yeah. I don't know what conjectures. Was it about the generation level, or was it about the singularity index? It's about how far the Hodge filtration is equal to the.
Yeah.
Yeah. Okay. So their papers were about hypersurfaces in projective space. Yes, and there it's very specific. So roughly speaking, if you have a hypersurface of degree d in Pn, it's something like n over d. Roughly speaking, like n over d. This index. Yeah, and that's basically what happens. I don't know. What I can say is that, for instance, if you take the cone over a hypersurface of degree d in Pn, right? You look at that singularity, then the minimal exponent there is exactly n over d. Yeah, so this is kind of the, yeah, that's basically the statement that I can make. So it's very much related to that. But in general, you know, you see, like, this is quite general and it's very useful. For instance, Saito showed that alpha tilde is bigger than 1 if and only if the divisor has rational singularities. So you see, as soon as you have some nice singularity conditions, then it gets better and better and better. Generational.
Other question, maybe, is there anything you can do with this Hooksbaum condition? So if you have Chronological, but there is a slightly weaker that you have that the local homologies are continuous. This help
I
me?
don't know. I'll take a look. I don't know. Does anyone know? I can tell you. You like two planes in A4 intersecting in one point. I don't know. So that's a good point. So in fact, you know, that's kind of what you use to give a kind of a bad example of like the Dubois complex, for instance. So I don't know. Do you know, Mitch? Yeah, it's a good question. Yeah, that's a good point. So anyways, you know, just for fun, since this is one maybe not quite related, but this is the example that okay, I'm gonna get this wrong, but this is the example that we were told. Okay, it wasn't our idea, but Lin Chuan Ma told us that this guy, where I took out the x squared y squared monomial, y the fourth. This guy is an example of a non-Cohen-Macaulay scheme where our criteria fail. So for instance, for this guy, the Hodge filtration is equal to the X filtration everywhere, but it's not Dubois. Ah. Yeah, exactly. Yeah, that's right. Yeah, okay, so maybe I should try to put this in context somehow. Yeah, so this is kind of a neat example.
So are there any more questions?
So you said that LCD is a topological invariant.
Yes.
And if you assume that Z doesn't have two bad singularities, for example, it's constant properly shifted is perverse, then there's another topological invariant where you can look at the length of this as a perverse or as a holonomic demodule. Is this related with the LCD?
I don't know. I don't know. It's possible. I mean, yeah, but I don't have a good answer. I mean, it sounds like it would provide some vanishing, but maybe some bound. Whether it computes it, I don't know. Sorry, I don't have a good answer. Maybe someone knows. Yeah. Yeah, actually, yeah, that's a good point. For hypersurface, it's always 1, so yeah. Right. Right. Yeah, that's a good point. I mean, yeah, simplest case should be much stronger than that. But maybe in general, it gives some bound.
So are there more questions? So maybe I have
Please.
to also look at the weight filtration.
You can. We did a little bit. by the way, this afternoon there will be a great talk on that. In the case of hypersurfaces by Sebastiano Lano, he will explain how you can do a very good theory in the case of hypersurfaces, like understanding most of these aspects. In higher codimension, we can say certain things, like you can actually look at the weight pieces and still understand them in terms of the this birational interpretation has a meaning. You put some weights on the forms with log poles, right? I mean, that's kind of where the weights come from. But we don't quite know what to do with it yet, right? I mean, we're still discovering in general what to do with the weight filtration, but at least you'll see a theory of weighted Hodge ideals. It's of course, this would be a great development to understand it well.
So let's think again.